Carbon is an essential element of all organic compounds. Carbon, which is tetravalent, has the ability to successively bond with other carbon atoms to form long chains or rings. The property of self-linkage of carbon atoms is known as catenation. Carbon also forms covalent bonds with hydrogen, oxygen, nitrogen, sulfur, and halogens. These carbon compounds are known as organic compounds. And the branch of chemistry that studies the formation and properties of organic compounds is known as organic chemistry. Organic compounds form the basis of life. For example, deoxyribonucleic acid, or DNA, is made up of sugar-like 2-deoxyribose and nitrogenous bases. In blood, muscles, and skin. Organic chemicals are also present in clothing, as in nylon fabric. In fuels, as a mixture of C7 to C9 hydrocarbons. In polymers, like polyethylene. In dyes, such as bromophenol blue. And in medicines, such as aspirin. In 1780, chemists discovered that organic compounds can be obtained directly or indirectly from plants and animals. While inorganic compounds are obtained from non-living resources such as minerals and rocks. In 1815, Berzelius, a Swedish chemist, suggested a theory which is known as the vital force theory. In his theory, he stated that organic compounds are produced only under the influence of some mysterious force existing in the living organisms. However, in 1828, Friedrich Wöhler, a German chemist, rejected the vital force theory. Wöhler synthesized an organic compound, urea, by heating an inorganic compound, ammonium cyanate. Later in 1845, Kolb synthesized acetic acid from purely inorganic compound. And in 1856, Berthelot synthesized methane from an inorganic compound. Thus, this led to the end of the vital force theory. A few years later, scientists found out that natural and synthetic organic compounds essentially contain carbon and hydrogen. And at times, they also contain other elements such as oxygen, nitrogen, sulfur, halogens, and phosphorus. Organic compounds made of only hydrogen and carbon atoms are known as hydrocarbons. All other organic compounds are considered to be derived from hydrocarbons by replacing one or more hydrogen atoms with atoms of other elements. Thus, organic chemistry is defined as the chemistry of hydrocarbons and their derivatives. The tetravalence of carbon can be explained from its valence shell electronic configuration. We know that the outermost shell of an atom is known as the valence shell. Electrons present in the valence shell, that is, valence electrons, take part in the chemical reaction. The electronic configuration of carbon is 1s2, 2s2, 2px1 and 2py1. This means that the valence shell has only 4 electrons. All elements tend to complete octet in their valence shell to become stable. Since carbon has 4 electrons in its valence shell, to complete its octet, the valence electrons of it form 4 covalent bonds with atoms of other elements. This characteristic of carbon atom, by virtue of which it forms 4 covalent bonds, is called as tetravalence of carbon. Thus, carbon forms a wide range of compounds. In this example, methane is formed by sharing 4 electrons of carbon with 4 hydrogen atoms. The formation of molecules and their shapes can be explained by considering the hybridization of s and p orbitals respectively. Now, let's look at how hybridization explains the shape of ethene molecule, that is, C2H4. In ethene, each carbon atom undergoes sp2 hybridization. 2 sp2 hybrid orbitals of each carbon atom overlaps with each of the 1s orbitals of 2 hydrogen atoms to form 2 sigma bonds respectively. The remaining sp2 hybrid orbital of a carbon atom overlaps coaxially with a similar sp2 hybrid orbital of the other carbon atom to form a strong carbon-carbon sigma bond by sp2-sp2 overlap. The unhybridized or pure 2pz orbitals of both the carbon atoms overlap laterally to form a weak carbon-carbon pi bond by pp overlap. Pi bond doesn't account for the shape of the molecule. All the 6 atoms forming the sigma bonds lie in one plane, and the pi bond lies perpendicular to the plane. Thus, the shape of the molecule is trigonal planar. Hybridization influences bond length and bond strength in organic compounds, which means that these parameters do influence the shapes of molecules. Among sp3, sp2 and sp, in an sp hybrid orbital, the s character is maximum, that is, 50%. Greater is the s character, closer is the orbital to the nucleus, and hence higher is the electronegativity of that carbon. Also, these effects result in shorter hybrid orbital, shorter bond length and greater bond strength of the bonds formed by sp hybrid orbital. In sp2 hybrid orbital, the s character is 33.3%, and in sp3 hybrid orbital, the s character is only 25%. Hence, the bond length is more in case of the bonds formed by sp3 than sp2 hybrid orbitals, and least in case of the bonds formed by sp hybrid orbitals. In sp2 hybrid orbitals, the s character lies between sp3 and sp hybrid orbitals. Hence, its bond strength and bond length is intermediate between them. Let's compare the CH bond lengths and the bond strengths in ethane, ethylene, and acetylene. Thus, bond strength of sp hybrid orbital is greater than sp2 followed by sp3 as shown here. And the bond length of sp3 hybrid orbital is greater than sp2 followed by sp as shown here. Thus, the greater the s character, the greater is the electronegativity. Sp is more electronegative, followed by sp2 and sp3. Now, let's look at certain characteristic features of a pi bond. The bonds formed by lateral overlapping of pure p orbitals are known as pi bonds. Let's look at the pi bonds in ethylene. Here, the pure p orbitals of both the carbon atoms, which are mutually parallel to each other, form a pi bond that is perpendicular to the plane of the molecule. Rotation of C around the double bond is strongly restricted, as the pi bonds prevent the free rotation around the carbon-carbon bond. In a pi bond, the electron charge cloud is present above and below the plane of the bonding atoms. Hence, these electrons are more exposed and susceptible to attack by electron-seeking reagents. In general, pi bonds provide the most reactive centers in unsaturated molecules. The pi electrons are more tightly held by the carbon atoms in acetylene, as the carbon atoms are sp hybridized compared to the pi electrons of ethylene, in which the carbon atoms are sp2 hybridized. Hence, acetylene is less reactive than ethylene. A chemical formula which represents the arrangement of atoms in a molecule is called the structural formula of a molecule. The various structures of organic compounds can be represented by 4 different ways. They are Lewis structural formula or dot structural formula, dashed structural formula, condensed structural formula, and bond line structural formula. Let's first look at the Lewis structural formula. The Lewis structure is named after the scientist Gilbert N. Lewis. In Lewis dot structure, a pair of electrons forming a covalent bond is represented by using a dot or cross. However, the Lewis dot structure can be further simplified by representing a pair of electrons by a dash. This simplified representation is called dash structure. Thus, a pair of electrons forming a single covalent bond is represented by a dash. A double covalent bond is represented by a double dash, and a triple covalent bond is represented by triple dash. Organic compounds containing heteroatoms with lone pair of electrons are represented by a pair of dots on the respective heteroatom. This structure represents the bonding between atoms in a molecule and also shows the presence of lone pairs present on the atoms, if any. This structural formula shows the arrangement of atoms and the type of bonds present between the atoms in the molecule. Here's the dash structural formula for ethane. In ethane, 2 atoms of carbon are attached to each other by a single covalent bond, and all carbon-hydrogen bonds are also single covalent bonds. In ethane, 2 atoms of carbon are connected with a double bond, and 2 hydrogen atoms are attached to each carbon by a single bond. In ethyne, 2 atoms of carbon are connected with a triple bond, and 1 hydrogen atom is attached to each carbon by a single bond. In methanol, carbon is attached to 3 hydrogen atoms and 1 hydroxyl group. 2 lone pairs of electrons present on the oxygen atom of hydroxyl group are represented as shown here. Now, let's look at the condensed structural formula. In a condensed structural formula, some or all the dashes that represent covalent bonds are omitted, and the number of identical groups attached to a carbon atom is represented by a subscript. Thus, a condensed structural formula is an abbreviated form of dash structure. The condensed formula of ethene, ethine, and methanol are represented as shown here. At times, the formula is further condensed by enclosing the repetitive structural unit within a bracket and placing an integer as a subscript, indicating the number of times the structural unit is repeated. In this case, CH2 is put within brackets and has a subscript of 6, indicating that the structural unit CH2 repeats 6 times. Finally, let's look at the bond line structural formula. A bond line structural formula is a short and simplified method for representing an organic compound. In this method, carbon-to-carbon bond is represented by lines drawn in zigzag fashion, represent carbon-to-carbon bonds, and line terminals generally represent methyl groups if they don't have a functional group, whereas the line junctions represent the carbon atoms attached to appropriate number of hydrogen atoms required to satisfy the valency of carbon. If any heteroatoms are present in place of hydrogens, they are specifically written by using their symbols as shown here. Let's consider the dash structural formula of 3-methyl octane. Now, let us represent the bond line structural formula for this as shown here. Here is the condensed structural formula and the bond line structure formula for 2-bromobutane. Cyclic compounds are represented by polygons. In a polygon, the corners represent a carbon atom and the sides represent a carbon-carbon bond. Symbol of atoms other than carbon and hydrogen are shown on the structure. Organic molecules can be represented by using the solid and dashed wedge formula. This is a 3-dimensional structural representation of an organic compound. This formula can be represented on the paper by using 3 conventions, that is, a dash, a solid wedge, and a dashed wedge. A dash is used to mean that the bond is in the plane of the paper. A solid wedge means that the bond is projecting out of the paper and is towards the observer. A dashed wedge is used to mean that the bond is projecting out of the paper and is away from the observer. The 3D image for the methane is shown here. 3-dimensional molecular models are used for better visualization and perception of the shapes of organic compounds. There are 3 types of molecular models: framework model, ball and stick model, and space filling model. In the framework model, the atoms are not shown. Only the bonds connecting the atoms of a molecule are shown. This model is used to study the patterns of bonds and does not consider the size of the atoms. In the ball and stick model, both bonds and atoms are shown. The balls represent atoms while sticks represent bonds. Compounds containing double bond, as in ethene, are represented in a different way. In place of a stick, a spring is used to represent the double bond. Hence, this type of model is called ball and spring model. Another type of molecular model is space-filling model. The relative size of each atom is based on van der Waals radius. That is, the volume occupied by each atom is shown. Bonds are not shown in this model. To simplify and systematize the study of organic compounds, they can be classified on the basis of their structure as open chain or acyclic compounds and closed chain or cyclic or ring compounds. Open chain compounds are also known as aliphatic compounds. The term aliphatic is derived from Greek word alipha, meaning fat or oil. The compounds in this class are derived from vegetable or animal fats. Open chain or acyclic compounds are compounds in which carbon atoms are linked by straight or branched chains. Some examples of straight chain compounds include butene, butine, pentyl alcohol, acetone. Some examples of branched chain compounds are isobutane, isobutylene. In a cyclic or ring or closed chain compound, the carbon atom and any other atom, if any, are joined together to form a closed ring. For example, in cyclohexane, 6 carbon atoms join together and form a closed ring. Cyclic compounds can be further classified as homocyclic or carbocyclic compounds and heterocyclic compounds. The word homo means same. Thus, homocyclic or carbocyclic compounds are those in which the ring consists of only carbon atoms. For example, in cyclohexane, the ring consists of only carbon atoms. The word hetero means different. Heterocyclic compounds are those in which the ring consists of carbon atoms. As well, the other atoms like sulfur, oxygen, or nitrogen. Homocyclic compounds can be further classified as alicyclic compounds and aromatic compounds on the basis of their characteristic properties. Homocyclic compounds, which resemble aliphatic compounds in their properties, are called alicyclic compounds or aliphatic cyclic compounds. An alicyclic compound consists of a ring which has only carbon atoms. For example, cyclopropane, cyclobutane, and cyclohexane. Aromatic compounds are benzene and the compounds that resemble benzene in their behavior. Aromatic compounds can be further classified as benzenoid compounds and non-benzenoid compounds on the basis of the presence or absence of benzene ring. Aromatic compounds containing isolated or one or more fused benzene rings and their functional derivatives are known as benzenoid aromatic compounds. Benzene is the parent compound in benzenoid derivatives. A non-benzenoid compound is one that does not contain a benzene ring. For example, tropolone as shown here. There is another class of aromatic compounds called heterocyclic aromatic compounds. These compounds contain heteroatoms such as nitrogen or sulfur or oxygen in addition to carbon atoms in the ring and resemble benzene in their properties. For example, pyridine, thiophene and furan are heterocyclic compounds containing heteroatoms, sulfur and oxygen respectively. The other way to classify the organic compounds is on the basis of functional groups. A functional group is an atom or a group of atoms present in a molecule, which determine its characteristic properties. For example, hydroxyl group and carboxylic acid group is the functional group of alcohols and carboxylic acids respectively. Organic compounds can also be classified on the basis of homologous series. The successive members or series of organic compounds with a characteristic functional group having the same general molecular formulae and differ by CH2 unit form a homologous series. The successive members of a homologous series are called homologs. For example, the homologous series of alkanes are methane, ethane, propane, butane, and so on. The successive members such as methane and ethane are called homologs. There are millions of compounds that fall under the branch of organic chemistry. To easily identify these compounds and their structure, scientists have assigned names to these compounds. The system of assigning a name to a compound is known as nomenclature. There are two systems for naming organic compounds: the common or trivial system and the IUPAC system. Let's look at the trivial system. The trivial names are given on the basis of the source and certain properties of organic compounds. For example, citric acid is named so as it is found in citrus fruits. Formic acid is named so as it is obtained from the destructive distillation of formica, which means red ants in Latin. This system was commonly used before 1892, and it did not follow any standardized rules. Moreover, more than one common name is given for certain compounds. To remember the common names given at random for large number of compounds that are discovered day to day is difficult. Hence, the need to develop a systematized method for naming organic compounds is found to be indispensable. Thus, in 1947, the IUPAC, that is the International Union of Pure and Applied Chemistry system of naming compounds, was first developed. The IUPAC system of nomenclature is a set of logical rules devised and used by chemists in which the name of a compound correlates to its molecular structure, thus making it intuitive for a person to deduce the structure from the name. However, common names are preferred for the IUPAC names, which are lengthy or complicated. Let's understand how IUPAC names are assigned to various compounds. The IUPAC name of an organic compound basically consists of three parts: the root word, the suffix, and the prefix. A root word indicates the length of the continuous selected carbon chain. A chain which consists of up to 4 carbon atoms is assigned special word roots based on the common names of alkanes. Thus, the word root for 1 carbon atom is meth, 2 carbon atoms is eth, 3 carbon atoms is prop, and 4 carbon atoms is but. A chain that consists of more than 4 carbon atoms is assigned a root word derived from the names of Greek numerals. Thus, the root word for 5 carbon atoms is pent, 6 carbon atoms is hex, 7 carbon atoms is hept, 8 carbon atoms is oct, 9 carbon atoms is non, and 10 carbon atoms is dec. Now let's look at the suffix. There are 2 types of suffixes: primary and secondary suffix. A primary suffix indicates the nature of the carbon chain that is saturated or unsaturated, and the secondary suffix indicates the functional group present in the compound. A primary suffix is added to the end of the root word. It indicates if a compound is saturated or unsaturated. That is, whether the compound consists of a single or multiple bonds. The 3 primary suffixes are ane for alkane, ene for alkene, and ine for alkyne. A secondary suffix indicates the nature of the functional group present in a compound. Thus, the 3 components can be combined to form part of the compound name. For example, the root word eth, primary suffix ane, and secondary suffix all together form the IUPAC name ethanol. A root word eth, primary suffix ane, and secondary suffix oic acid together forms the IUPAC name ethanoic acid. If a functional group is present, then E of the primary suffix is replaced by the secondary suffix. Now let's look at the final component, the prefix. There are 2 types of prefixes: primary prefix and secondary prefix. A primary prefix is used to differentiate acyclic and cyclic compounds. However, the rules for using these are slightly different. For example, in cyclic compounds, the prefix cyclo is added before the root word. In the IUPAC system, some groups are not considered as functional groups. They are treated as substituent groups. In such cases, the substituent acts as the secondary prefix. Some secondary prefixes and their substituent groups are fluoro for fluorine, chloro for chlorine, bromo for bromine, iodo for iodine respectively. However, in acyclic compounds, the primary prefix is not used. So, if the prefix cyclo is not used, it indicates that the compound is acyclic, as in propane. We know that hydrocarbons are organic compounds that contain only carbon and hydrogen. The hydrocarbons, which consist of carbon-carbon single bonds, are said to be saturated and are called alkanes. The general formula for alkanes is CnH2n plus 2, where N indicates the number of carbon atoms. We know that there are two systems for naming organic compounds, the common or trivial system and the IUPAC system. The names of the first four members of alkanes are based on the trivial names. They are methane, ethane, propane and butane. The IUPAC name of an alkane basically consists of two parts, the root word and the suffix. A root word indicates the length of the continuous selected carbon chain. A chain which consists of up to 4 carbon atoms is assigned special root words from their trivial names. Thus, the root word for 1 carbon atom is meth, 2 carbon atoms is eth, 3 carbon atoms is prop, and 4 carbon atoms is bute. A chain that consists of more than 4 carbon atoms is assigned a root word derived from the names of Greek numerals. Thus, the word root for 5 carbon atoms is pent, 6 carbon atoms is hex, 7 carbon atoms is hept, 8 carbon atoms is oct, 9 carbon atoms is non, and 10 carbon atoms is dec. A suffix indicates the nature of the carbon chain. As the carbon chain is saturated, suffix ane is used. For example, a compound that has 2 carbon atoms in the chain will have the root word eth and the suffix ane. Thus, its IUPAC name will be ethane. Similarly, the IUPAC name of an alkane having 4 carbon atoms is thus bute plus ane, butane. Alkanes can be straight chain alkanes or branched chain alkanes. Let's look at the IUPAC names of certain straight chain homologues of alkane series. The IUPAC name of an alkane having 1 carbon atom is methane. The IUPAC name of an alkane having 2 carbon atoms is ethane. The IUPAC name of an alkane having 3 carbon atoms is propane. The IUPAC name of an alkane having 4 carbon atoms is butane. The IUPAC name of an alkane having 5 carbon atoms is pentane, and so on, as shown here. Let's look at the trivial and IUPAC names of the branched chain alkanes. Small chains of carbon atoms attached at 1 or more carbon atoms of the parent chain is said to be a branched chain. These small chains of carbon atoms are called alkyl groups. Let us briefly study about the alkyl groups. The group which consists of 1 hydrogen atom less than an alkane is called an alkyl group. For example, if 1 hydrogen atom is removed from methane, that is CH4, we get the alkyl group CH3. An alkyl group is named by replacing the ane in the name with YL. Thus, the name of alkyl group of methane will be methyl. At times, abbreviations are used for certain alkyl groups. For example, methyl is abbreviated as Me, ethyl is abbreviated as Et, propyl is abbreviated as Pr, and butyl is abbreviated as But. Alkyl groups are called as primary, secondary, or tertiary based on whether 1, 2, or 3 other carbon atoms are directly attached to the carbon atom in the chain. Alkyl groups derived from the saturated hydrocarbons having minimum 3 or more carbon atoms can have the following possible branched structures. For example, propyl and butyl groups can have the following structures. The trivial names given for these structures are isopropyl, secondary butyl, and tertiary butyl, as the carbon atom is attached to other 2 and 3 carbon atoms respectively. Now let us see how in the trivial system the various straight chain and branched chain alkanes such as butane and pentane are differentiated. If all the carbon atoms form a continuous straight chain, that is, without branching, then the prefix N is given to the name of the alkane. For example, for the structure shown here, which consists of a continuous chain of 5 carbon atoms, the name given is N-pentane. If the carbon atom next to the terminal carbon having a methyl group as a branch is attached to a continuous carbon chain, then a prefix iso is given to the name of the alkane. For example, for the structure shown here, which consists of a branched chain and is a 5-carbon system, the name given is isopentane. If the carbon atom next to terminal carbon has 2 methyl groups as branches, is attached to a continuous carbon chain, and then a prefix neo is given to the name of alkane. For example, for the structure shown here, which consists of 2 branched chains and is a 5-carbon system, the name given is neopentane. The corresponding alkyl groups are named as N-alkyl, isoalkyl, neoalkyl respectively. Examples of N-alkyl, isoalkyl, and neoalkyl are shown here. They are N-pentyl, isopentyl, and neopentyl respectively. Now let us look at the IUPAC rules to name the branched chain alkanes. Rule 1. Select the longest carbon chain in the molecule. In this compound, the longest chain consists of 9 carbon atoms. Hence, it is also called as parent chain or root chain. Selecting the longest chain as in second case is not correct because the parent chain consists of only 8 carbon atoms. Rule 2. Number the parent chain that has branches. The numbering of the chain is done in such a way that the branched carbon atoms get the lowest possible number. If we number the chain from left to right, then the branches are located at carbon 2 and 6. And if we number the chain from right to left, then the branches are located at carbon 4 and 8. As per the rule 2, the numbering should be done from left to right. Rule 3. Name the branched chain alkane. The name of the alkyl group attached to the carbon atom as a branch, that is, a substituent, is given the appropriate prefix to the name of the parent alkane, and the position of the alkyl group on the parent chain is indicated by writing the appropriate number. If more than one alkyl substituent is present, then the names of alkyl groups are listed in alphabetical order. For example, in this compound, the alkyl groups methyl and ethyl are fixed to the alkane nonane in the alphabetical order, and positions of the substituents are 2 and 6. Hence, the name of the compound is 6-ethyl 2-methyl nonane. The numbers are separated from the alkyl group name by using a hyphen. Rule 4. Name the identical alkyl groups at different positions of the carbon chain using the prefixes di, tri, tetra, etc. If more than one identical alkyl group is present on the parent carbon chain, at different positions, prefixes such as di for 2 identical alkyl groups, tri for 3 identical alkyl groups, tetra for 4 identical alkyl groups, etc. are used with the alkyl group. For example, while naming the following compound that has 2 methyl substituents at 2 and 4 positions, the prefix di is used. Hence, the name of the compound is 2,4-dimethyl-pentane. Similarly, prefix tri is used while naming the following compound. Hence, the name of this compound is 2,2,4-trimethyl-pentane. The position numbers of the substituents are separated by comma. Note that the prefixes di, tri, etc. are not considered when deciding the alphabetical order of the alkyl groups. In the following compound, the ethyl group name is written first as per alphabetical order, ignoring the prefix di used for methyl group. Rule 5. Numbering different alkyl groups at equivalent positions. If 2 substituents are present on equivalent positions, then the lower number is assigned to the group that appears first in the alphabetical listing. For example, in case 1, the ethyl group is present on carbon 3, which is assigned a lower number than its position at 6 in case 2. Hence, the correct name for the compound would be 3-ethyl 6-methyl octane. Rule number 6. Numbering the complex substituent. If the substituent, that is, the alkyl branch on the parent chain, is complex, then the carbon atom of the branch attached to the parent chain is given the position 1 while numbering as shown. The name of this alkyl branch is placed in the parenthesis while naming the compound. The use of prefixes such as iso, secondary, tertiary for naming the substituents, that is, the alkyl groups, is allowed in the IUPAC nomenclature, but such alkyl groups should not be further substituted. Iso and neo are considered, but secondary and tertiary are not considered to be part of the fundamental name of alkyl groups during writing the names in an alphabetical order. The parent chain, which contains more number of side chains, is selected. The chain highlighted in red has 3 side chains attached to it. If we select the other chain, as shown as the parent chain, it will have only 2 side chains attached. Hence, case 1 is the correct way to select the chain. The chain should be numbered from the end which is closer to the alkyl groups. Here, the alkyl groups are attached to carbon 3 and 5. Here, the substituents are attached to carbon 6 and 8. So, it is far from the substituent. Hence, it is a wrong way of numbering. Then, the substituent groups are numbered. As there are 4 carbon atoms present, the alkyl group is butyl. The ethyl group is attached to the second carbon atom. Hence, the name of the substituent is 2-ethyl-butyl. The substituent 2-ethyl-butyl is attached to the 5th carbon atom of the parent chain. Hence, it is 5-2-ethyl-butyl. Here, 2-ethyl-butyl is written in parentheses. The parent chain consists of 10 carbon atoms. Hence, it is decane. 2 methyl groups are attached to the 3rd carbon atom. Hence, their name will be 3,3-dimethyl. The name of the compound will be 5-2-ethyl-butyl 3,3-dimethyl decane. Now let's look at the nomenclature for the cyclic compounds, also known as cycloalkanes. Cycloalkanes are saturated compounds containing a ring of carbon atoms. They are named by adding the prefix cyclo to the corresponding straight chain alkane. For example, in a ring consisting of 5 carbon atoms, the prefix cyclo is added to pentane. Hence, the name of the compound is cyclopentane. If different alkyl groups are present in a cyclic compound, then the names are written in alphabetical order. For example, in the following compound, as per the alphabetical order, methyl group comes first, followed by propyl. Hence, the name of the compound is 1-methyl-3-propyl cyclohexane. This cyclic compound consists of 6 carbon atoms in a ring. Hence, it is cyclohexane. The compound is numbered from right to left. The ethyl group is attached to the 3rd position of the cyclohexane, and 2 methyl groups are attached at position 1. Hence, the name of the compound would be 3-ethyl-1,1-dimethyl cyclohexane. If the compound is numbered from left to right, then 2 methyl groups are attached at 3rd position. This means that the more branching is at the 3rd carbon atom, and the name of the compound would be 1-ethyl-3,3-dimethyl cyclohexane. This is incorrect. We've learned that a functional group is an atom or a group of atoms present in a molecule, which determines the characteristic properties of the molecule. For example, methanol, ethanol, and propanol all contain the hydroxyl functional group. All these compounds react with sodium metal and liberate hydrogen. Thus, we can conclude that organic compounds that have similar functional groups show similar chemical reactions. Functional groups play an important role in determining the properties of a compound and are used to organize organic compounds in different classes. Based on the structure of the compounds, they have been organized into classes and assigned IUPAC group prefix and suffix. The alkane group suffix is ane, A-N-E. The alkene group suffix is ene. The alkyne group suffix is ine. The halide group prefix is halo. The alcohol group prefix is hydroxy and the group suffix is ol. The aldehyde group prefix is formyl or oxo and the group suffix is al. The ketone group prefix is oxo and the group suffix is on. The nitrile group prefix is cyano and the suffix is nitrile. The ether group prefix is alkoxy. The carboxylic acid group prefix is carboxy and the suffix is oic acid. The carboxylate ion group suffix is OAte. The ester group prefix is alkoxycarbonyl and the suffix is OAte. The acyl halide group prefix is halocarbonyl and the suffix is oil halide. The amine group prefix is amino and the suffix is amine. The amide group prefix is carbamoyl and the suffix is amide. And the nitro group prefix is nitro. The sulfonic acid's prefix is sulfo and the group suffix is sulfonic acid. Now let's see how we can use the prefix and suffix to assign names to compounds. Step 1. Identify the functional group in the compound. In this example, the functional group OH belongs to the class alcohol. As per the IUPAC system, the suffix for the alcohol group is OL. Step 2. Number the longest chain. If we number the chain from right to left, then the OH group is on second position. And if we number the carbon chain from left to right, then the OH group is on fourth position. As per the naming convention, functional group should be attached to the carbon atom with the lowest possible number. Hence, case 1 is the correct way of numbering. Step 3. Assign a root word. As there are 5 carbon atoms in the chain, the root word will be pent. Step 4. Assign a primary suffix. The chain only contains single bonds. Hence, the primary suffix will be ane. Step 5. Assign a secondary suffix. The functional group is OH, that is alcohol. Hence, the secondary suffix will be ol, OL. Step 6. Specify the position of the functional group. The functional group OH is present at the second position. Hence, the position of the functional group will be 2. Thus, the name of the compound is pentan-2-ol. But some compounds have more than one functional group. These are known as polyfunctional compounds. In such compounds, one of the functional groups is chosen as the principal functional group. The principal functional group is selected based on the order of decreasing priority as shown here. Carboxylic acid has the highest priority, followed by sulfonic acid. Esters, alkyl halides, amides, nitriles, aldehydes, ketones, alcohols, amines, alkenes, and alkynes. In the given compound, carboxylic acid will be the principal functional group, as it has higher priority than the ketone functional group. The name of the compound is written on the basis of the principal functional group. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the principal functional group is attached. The principal functional group will come as a suffix. For carboxylic acid, the suffix oic acid is used. The other functional groups act as substituents, and they are written by using appropriate prefixes. Here, the substituent is ketone, and the prefix used for ketone is oxo. Thus, the name of the compound is 5-oxohexanoic acid. If the same functional group appears more than once in a compound, we name the compound by adding di, tri, etc. before the suffix, and the full name of parent alkane is written before the suffix. In this case, since two carbons are present, therefore the word root is eth. A single bond is present, therefore the prefix is ane. Hence, the name of the compound is ethane 1,2-diol. Now let's name this compound. In this compound, there are two functional groups attached, nitrile group and alcohol group. As the nitrile group has higher priority than alcohol group, we will number the carbon chain such that the carbon of nitrile group gets position 1. Hence, the name of the compound will be 3-hydroxy-4-methyl-pent 4-ene-1-nitrile. The terminal E of the parent chain is retained as it is followed by a consonant and not by a vowel or Y. On the other hand, in the next compound shown here, there is a double bond and a triple bond. In IUPAC nomenclature of organic compounds, a double bond gets preference over a triple bond. Hence, the name of the compound will be pent 3-ine-1-ene. Monosubstituted benzene has only one substituent attached to the benzene ring. While writing the IUPAC name of the monosubstituted benzene, the substituent's name is placed as a prefix to the word benzene. For example, in this compound, the substituent is nitro. Hence, the name of the substituent, which is nitro, is placed as a prefix to the name of the parent compound benzene, and the name of the compound becomes nitrobenzene. Similarly, if the substituent is bromine, then the name of the compound is bromobenzene. Now let us name the following monosubstituted benzenes having the substituents methyl, methoxy, amino, and hydroxy respectively. The names of these compounds are methylbenzene, methoxybenzene, aminobenzene, and hydroxybenzene. The common names for these compounds are also widely in use. The common names for these compounds are toluene, anisole, aniline, and phenol respectively. Now let us discuss the nomenclature of the benzene that has more than one substituent. If more than one substituent is present, then the positions of the substituents are indicated by numbering the carbon atoms of the ring. The numbering is done in such a way that the sum of the locants is the least. This means that the substituents should be located at the lowest numbers possible. Let us understand this by considering the following two cases. In case 1, the carbon atoms are numbered in the clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 3. In case 2, the numbering of carbon atom is done in the anti-clockwise direction. As a result, the two bromine atoms are present at the positions 1 and 5. According to the rule, case 1 follows the correct way of numbering. 3 isomers are possible for a di-substituted benzene. These 3 isomers are differentiated in the trivial system by using the names ortho, para, and meta, which are abbreviated as O, P, and M respectively. The positions of the substituents in a di-substituted benzene is thus indicated by using the appropriate prefix ortho, meta, or para. When the substituents are present on the adjacent positions of the benzene ring, that is, on the first and second positions, then in the IUPAC system of nomenclature, the positions of these substituents are indicated as 1, 2, and in trivial system, the prefix ortho is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 2 positions. Hence, the name of the compound is 1,2-dibromobenzene or ortho-dibromobenzene. When the substituents are present at the alternate position of the benzene ring, that is, on the first and third positions, then, in the IUPAC system, the positions of these substituents are indicated as 1, 3, and in the trivial system, the prefix meta is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 3 positions. Hence, the name of the compound is 1,3-dibromobenzene or meta-dibromobenzene. When the substituents are present on diagonally opposite positions of the benzene ring, that is, at 1 and 4 positions, then, in the IUPAC system, the position of these substituents are indicated as 1, 4, and in the trivial system, the prefix para is used as shown here. For example, in this compound, the substituent bromine is present at 1 and 4 positions. Hence, the name of the compound is 1,4-dibromobenzene or para-dibromobenzene. Similarly, the names of the following compounds with 2 different substituents on the benzene ring are 2-ethyl-anisole or ortho-ethyl-anisole and 4-nitroaniline or para-nitroaniline respectively. Now let's look at the nomenclature of tri or higher substituted benzene. Tri-substituted benzene has 3 substituents attached to the benzene ring. Let's look at the rules for naming such compounds. Trivial system of nomenclature cannot be employed as it has more than 2 substituents. This compound has 3 bromine groups attached to the benzene ring. If more than 2 substituents are present, then the positions of the groups are indicated by numbering the carbon atoms according to the lowest locant rule. This means the sequence in which the numbering is done should have the lowest combination of numbers. If the carbon atoms are numbered in the clockwise direction, then the bromine substituent is found at positions 1, 2, and 4. If the carbon atoms are numbered in the anticlockwise direction, then the bromine substituent is found at positions 1, 4, and 6. Hence, according to the lowest locant rule, the correct way of numbering is followed in case 1. Thus, the name of the compound is 1,2,4-tribromobenzene. In this compound, there are 3 different substituents attached to the benzene ring. According to lowest locant rule, the substituent positions in the ring are identified. Hence, the name of the compound is 1,chloro,2,4-dinitrobenzene and not 4-chloro,1,3-dinitrobenzene. In certain cases, the common name of the benzene derivative is taken as the base compound. Thus, anisole is a base compound in the following structure. The numbering of the carbon atom starts from the carbon bearing substituent of the base compound. Thus, the carbon bearing substituent of the base compound, methoxy, is assigned the number 1. Then, the direction of numbering is chosen in such a way that the next substituent gets the next lowest number. In case 1, the numbering is done in the clockwise direction. Thus, the next substituent gets the position 2. Hence, the positions of the substituents present are 1, 2, and 4. In case 2, the numbering is done in the anticlockwise direction, and the substituents get the positions 1, 4, and 6. As per the lowest locant rule, case 1 is the correct way of numbering. Thus, the name of the compound is 2-chloro-4-methylanisole. Note that the names of the substituents are written in alphabetical order. Thus, chloro comes first, followed by methyl. In this compound, the benzene ring is attached to an alkane with a functional group. In such cases, the benzene ring is considered as a substituent. The name of the benzene ring, when it acts as the substituent, is phenyl. The phenyl group is written as C6H5 or abbreviated as PH. The 2 bromine atoms act as the functional groups. The alkane is numbered as per the lowest number rule. In case 1, the carbon atoms are numbered from left to right. As a result, the substituent and the functional group are assigned the positions 1, 2, and 3. In case 2, the carbon atoms are numbered from right to left. As a result, the substituent and the functional group are assigned the positions 3, 4, and 5. According to the lowest locant rule, case 1 follows the correct way of numbering. Bromine is attached to the second and third carbon atoms, hence should be named as 2,3-dibromo. Phenyl is attached to the first carbon atom, hence should be named as 1-phenyl. The alkane has 5 carbon atoms, hence should be named as pentane. Thus, the name of the compound is 2,3-dibromo-1-phenylpentane. Let's take a compound with the molecular formula C4H10 to understand this concept. If we were to draw the structure of C4H10, we could draw it in the 2 ways shown here. Both the compounds have same number of atoms, that is, 4 carbon atoms and 10 hydrogen atoms. Thus, their molecular formula is the same. The name of the first compound is N-butane and the second compound is isobutane or 2-methylpropane. Both these compounds have different properties. The phenomenon of existence of two or more compounds with the same molecular formula but with different properties is known as isomerism, and the compounds are called isomers. Thus, N-butane and isobutane are isomers. Isomerism can be of two types: structural isomerism and stereoisomerism. The compounds that have the same molecular formula but different structures are known as structural isomers, and the phenomenon is known as structural isomerism. For example, in N-butane and isobutane, the molecular formula is same but their structures are different. Thus, they are structural isomers. Structural isomerism can be of following types: chain isomerism, position isomerism, functional group isomerism, and metamerism. Let's look at chain isomerism. Compounds that have the same molecular formula but different carbon chain, that is, straight or branched chain, are known as chain isomers, and the phenomena is known as chain isomerism. For example, the following three chain isomers are possible with molecular formula C5H12. They are N-pentane, isopentane or 2-methylbutane, and neopentane or 2,2-dimethylpropane. Here the carbon skeleton is different in each compound, but the molecular formula is the same. Now, let's look at position isomerism. Compounds that have the same molecular formula, same chain, but which differ in the position of the substituent or functional group are known as position isomers, and the phenomenon is known as position isomerism. For example, the molecular formula C3H8O represents two position isomers. In case 1, the functional group OH is attached to the first carbon atom. Hence, the name of the compound is propan-1-ol. In case 2, the functional group OH is attached to the second carbon atom. Hence, the name of the compound is propan-2-ol. In both the compounds, the molecular formula is same, but the position of the functional group differs. Next, let's look at functional group isomerism. Compounds that have same molecular formula but different functional groups are known as functional isomers, and the phenomena is known as functional isomerism. Propanone and propanal represent two functional isomers having the same molecular formula, C3H6O. Here the functional group differs. That is, in case 1, ketone is the functional group, and in case 2, aldehyde is the functional group. Some examples of functional isomers are alcohols and ethers, cyanides and isocyanides. Finally, let's look at metamerism. Compounds that have the same molecular formula but different alkyl groups attached to the same functional group are called as metamers, and the phenomena is known as metamerism. This type of isomerism occurs due to the difference in the nature of alkyl group attached to the functional group. Metamers always belong to the same homologous series. Let's consider the molecular formula C4H10O. The following isomers can be drawn, that is, methoxypropane and ethoxyethane. Here the alkyl group attached on either side of the functional group is different. In case 1, methyl and propyl are attached to either side of the functional group, and in case 2, ethyl groups are attached to either side of the functional group. Metamers may also be regarded as positional isomers. Some metamers are ethyl aminoethane and methyl aminopropane, 2-pentanone and 3-pentanone. Now let's look at stereoisomerism. In Greek, stereo means space and meros means parts. The isomers which possess the same structural formula but differ in three-dimensional arrangement of atoms or groups in space within the molecule are known as stereoisomerism, and the phenomenon is called stereoisomerism. Stereoisomerism can be of two types: geometrical isomerism and optical isomerism. You'll learn about these stereoisomer types in higher classes. In an organic reaction, when reactants react to form a new compound, the reactant that supplies the carbon atom for the formation of a new bond or to the reactant on which the focus is called the substrate, whereas the other reactant in the reaction is called the reagent. In the reaction between chlorine and methane, methane supplies the carbon atom to form chloromethane. Hence, methane is the substrate and chlorine, the other reactant, is the reagent. Covalent bond between carbon and bromine of methyl bromide gets cleaved and a new bond between carbon and hydroxide ion is formed. The energetics during breaking and forming of bonds, movement of electrons, and the rate of reaction in a sequential description are referred to as the reaction mechanism. Let's study each step in detail. A covalent bond can get cleaved either by homolytic cleavage or by heterolytic cleavage. In homolytic cleavage, a bond breaks equally in such a way that each atom gets one electron of the shared pair. A fishhook or half-headed arrow is used to show the movement of a single electron. Homolytic cleavage results in the formation of neutral atoms or groups with one unpaired electron. These are known as free radicals. The free radicals thus formed are highly reactive due to the presence of unpaired electrons. For example, the homolytic cleavage of the chlorine-chlorine bond in chlorine molecules, induced by heat or light, leads to the formation of two chlorine free radicals. Depending on the number of alkyl groups directly attached to the carbon free radical, alkyl free radicals are classified as primary, secondary, and tertiary. Greater is the number of alkyl groups, greater is the stability. Hence, primary alkyl radicals are the least stable, while tertiary radicals are the most stable. The organic reactions preceded by homolytic fission producing free radicals are called free radical or homopolar or non-polar reactions. Heterolytic cleavage is just the opposite of homolytic cleavage. In heterolytic cleavage, a bond is broken unequally, and the shared electron pair goes to the more electronegative atom. Thus, after heterolytic cleavage, the atom that loses the bonded electrons gets a sectet, electronic structure, and acquires a positive charge. For example, in the heterolytic cleavage of bromomethane, the shared electron pair goes to the bromine atom, leading to the formation of a bromide anion and a methyl cation. A positively charged carbon with a sectet, which is the methyl cation here, is called a carbocation or a carbonium ion. Carbocations are very reactive as they have a strong tendency to complete their octet. Depending on the number of alkyl groups directly attached to the positively charged carbon, carbocations are classified as primary, secondary, and tertiary carbocations. For example, ethyl cation is a primary carbocation, while isopropyl carbocation and tert-butyl carbocations are secondary and tertiary carbocations respectively. Stability of the carbocations increases with increase in number of alkyl groups bonded to the carbocation. Hence, primary carbocations are highly unstable, while tertiary carbocations are the most stable. In methyl carbocation, 3 sp2 hybridized carbon orbitals overlap with the 1s orbital of each of the 3 hydrogen atoms. The remaining 2p orbital of carbon is vacant and lies perpendicular to the molecular plane. Therefore, the shape of the carbocation is trigonal planar. There are also heterolytic cleavages where the carbon gets the shared pair of electrons. For example, the removal of the hydrogen ion in the presence of a base from the methyl part of an acetaldehyde molecule leaves both the carbon-hydrogen bond electrons on carbon. Such a chemical species bearing a negative charge on carbon atom and possessing 8 electrons in its valence shell are called carbanions. Carbanions also are classified as primary, secondary, and tertiary carbanions, depending on the number of alkyl groups attached to the negatively charged carbon. Stability of the carbanions decreases with increasing number of alkyl groups bonded to the charge-bearing carbon atom. Hence, tertiary carbanions are highly unstable, while primary carbanions are the most stable. The shape of a carbanion is tetrahedral. All the organic reactions preceded by heterolytic bond cleavage are known as ionic or heteropolar or polar reactions. Polar organic reactions are caused by two types of reagents: electrophiles and nucleophiles. Electrophile is an electron-seeking or electron-loving species, as it is electron-deficient. Electrophiles may be either positively charged, such as carbocations, hydrogen ion and hydronium ion, or electrically neutral species, such as boron trifluoride, aluminium chloride, ferric chloride, and carbonyl group. A reaction initiated by an electrophile is called an electrophilic reaction. Electrophiles always attack the substrate molecule at the site of maximum electron density. An electron-rich reagent that donates electrons to the positive or electron-deficient site in a compound is called a nucleophile. A nucleophile is a nucleus-loving species, as it is electron-rich. Negatively charged species with lone pairs of electrons, such as hydroxide, chloride, cyanide ions, and carbanions, and molecules such as water, ammonia, and lithium aluminium hydride are some of the neutral nucleophiles. A reaction initiated by a nucleophile is called a nucleophilic reaction. Nucleophiles always attack the substrate molecule at the site of minimum electron density. The movement of an electron pair in organic reactions is denoted by a curved arrow. The curved arrow starts from the point where an electron pair is shifted and ends at the final location where the pair of electrons may move. For example, electron flow from a pi bond to the adjacent bond position, or from a pi bond to the adjacent atom, or from an atom to the adjacent bond position may be represented as follows. You have already learned that most of the attacking reagents carry either a positive or a negative charge. Hence, for a reaction to take place on the substrate, it must possess oppositely charged centers. This is made possible by the partial or complete displacement of the bonding electrons. The factors which influence the electron density in the substrate are inductive effect, resonance effect, electromeric effect, and hyperconjugation. Let's understand each type one by one. In the case of a covalent bond between two atoms of different electronegativity, the electron density shifts more towards the more electronegative atom of the bond. The electron shift polarizes the covalent bond, leading the more electronegative atom to acquire a partial negative and less electronegative atom to acquire a partial positive charge. The fractional electronic charges in a polar covalent bond are denoted by delta positive and delta negative, and the shift of the electron density is shown by an arrow that points from delta positive to delta negative end of the polar bond. For example, in chloroethane, chlorine is more electronegative than carbon. Hence, the electron pair shared between carbon and chlorine is displaced towards the chlorine atom. Thus, a partial negative charge is acquired by chlorine and a partial positive charge is acquired by carbon. The partial positive charge on C1 draws some electron density towards itself from the adjacent carbon-carbon bond. This causes C2 to acquire a small positive charge. The delta plus represents a relatively smaller positive charge as compared to that on carbon 1. Thus, carbon-chlorine bond induces polarity in the adjacent bonds. Such polarization of a sigma bond caused by the polarization of an adjacent sigma bond is called inductive effect. Inductive effect decreases as the distance from the source atoms increases. The inductive effect is related to the ability of a group to either withdraw or donate electron density to the attached carbon atom of the alkyl group. If any atom or group attracts electrons more strongly than hydrogen, it is classified as electron withdrawing group and is said to have a minus inductive effect. On the other hand, if any atom or group attracts electrons less strongly than hydrogen does, then it is classified as electron donating group and is said to have plus inductive effect. Halogens, nitro, cyano, carboxy and ester groups are electron withdrawing or minus inductive effect groups. Alkyl groups, for example, methyl and ethyl, are electron donating or plus inductive effect groups. Now, let's learn about another important electronic effect called the resonance effect. Resonance refers to the phenomenon where two or more structures can be written for a molecule or an ion. Because of resonance, the electronic charge spreads over the entire molecule and hence affects its polarity. If the polarity of a molecule is developed either by the transfer of electrons between two pi bonds or from a lone pair to a pi bond in conjugation, creating high and low electron density due to resonance, then this phenomenon is called the resonance effect or mesomeric effect, which is designated as R or M effect. Resonance effect is of two types. They are positive resonance effect and negative resonance effect. In the positive resonance effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Halogens, amino group, hydroxyl group, and methoxy group are some of the examples of positive resonance effect groups. The positive resonance effect in monosubstituted benzene increases the electron density at ortho and para positions. For example, in aniline, due to the conjugation of lone pair of electrons on the nitrogen of the amino group with the pi electrons of benzene, the electron density is increased at the ortho and para positions as shown here. When the electron shift takes place in the direction of the atom or substituent group attached to the conjugated system, it is called the negative resonance effect. Nitro group, cyano group, and carbonyl group are some of the examples of negative resonance effect groups. The negative resonance effect decreases the electron density at ortho and para positions in the molecule. For example, in nitrobenzene, as nitrogen withdraws electron density from the ortho and para positions in the benzene ring, the electron density decreases at those positions as shown here. Now, let us look at the electromeric effect. It is a temporary effect and observed only in organic compounds with multiple bonds in the presence of an attacking reagent. Electromeric effect may be defined as the complete transfer of the shared pair of pi electrons of multiple bonds to one of the atoms in the presence of an attacking reagent. It is important to note that this effect ceases to exist as soon as the attacking reagent is removed from the domain of the reaction. This effect is represented by E, and the shifting of the electrons is shown by curved arrow. There are two types of electromeric effects, positive and negative. In the positive electromeric effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent is bonded. For example, in the addition of acids to alkenes, the pi electrons of the double bond are transferred to that carbon to which the attacking reagent is bonded. On the other hand, when the pi electrons of the multiple bond are transferred to the atom to which the attacking reagent does not get attached, it is called negative electromeric effect. In the addition of cyanide ion to alkenes, the pi electrons of the double bond are transferred to that atom to which attacking reagent does not get attached. Let's learn what hyperconjugation is and how it affects the stability of the various species in detail. A general stabilizing interaction which involves the delocalization of sigma electrons of a CH bond of an alkyl group directly attached to an unsaturated system or to a species with an unshared p orbital, such as carbocations or free radicals, is known as hyperconjugation. Hyperconjugation is a permanent effect. Let us take the example of ethyl carbocation to explain this effect. In ethyl cation, the positively charged carbon atom has an empty p orbital. One of the carbon-hydrogen bonds of the methyl group aligns in the same plane with the empty p orbital of the positively charged carbon atom. The electrons of this carbon-hydrogen sigma bond then get delocalized into the empty p orbital as shown here. In carbocations, this delocalization of electrons helps in dispersing the positive charge on the carbocation to the adjacent atoms and stabilizes it. Thus, the carbocation is stabilized by hyperconjugation. Greater the number of alkyl groups attached to a positively charged carbon atom, greater is the hyperconjugation interaction and stabilization of the cation. Hence, the tertiary carbocation in which there are three alkyl groups attached to the positive carbon is more stable than a secondary carbocation with two alkyl groups. Similarly, a secondary carbocation is more stable than a primary carbocation. Therefore, the order of stability decreases from tertiary carbocation to methyl cation. Hyperconjugation also explains the stability of certain olefins over other halides. For example, propene is more stable than ethene because in propene there are 3HC hyperconjugated bonds which lead to greater stability. If you observe the resonating structures of propene, you can see that there is no definite bond between the carbon atom of the methyl group and one of the hydrogen atoms. Hence, hyperconjugation is also known as no-bond resonance. Based on the nature of organic compounds and the impurities present in them, organic compounds can be purified using 5 different methods. These are sublimation, crystallization, distillation, differential extraction, and chromatography. In this module, we will look at the first three methods. Sublimation technique is used to purify sublimate solid organic compounds. You have learned that sublimation is a process which involves the conversion of a solid directly into vapor without any intermediate liquid state. This process is used for separating sublimable compounds from non-sublimable impurities. In this process, the impure substance is heated in a dish covered with a perforated filter paper over which an inverted funnel is placed. The stem of the funnel is plugged with a little cotton. Vapors of the solid, which sublime, pass through the holes in the filter paper and condense on the cooler walls of the funnel. The non-volatile impurities are left behind in the dish. Iodine, camphor, naphthalene and benzoic acid are purified by this method. Now let's look at the next method of purification, called crystallization. It is one of the most commonly used techniques for the purification of solid organic compounds. This technique is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. In this process, first, the impure compound is dissolved in a solvent in which the compound to be purified is moderately soluble at room temperature and highly soluble at higher temperature. The solution is heated to get a nearly saturated solution. This saturated solution is then cooled to obtain the compound in its pure crystal form. The crystals are separated out from the filtrate by the filtration technique. The crystals are washed once or twice with small quantities of the pure solvent and dried by pressing between the folds of filter paper and then placed in an air oven. Sometimes impurities impart color to the solution. To remove such impurities, the filtrate is passed through activated charcoal. The charcoal adsorbs the impurities. The solution is then filtered and recrystallized as described above. Now let's look at the distillation process. This method is used for separating volatile liquids from non-volatile impurities, and also to separate the liquids which differ in their boiling points. Simple distillation is used when the liquids in the mixture differ appreciably in their boiling points. For example, a mixture of chloroform and aniline, which differ in their boiling point by 123 degrees Celsius, are separated by this technique. In this method, the liquid mixture is taken in a round bottom flask which is fitted to a Liebherr condenser and heated. On heating, the vapors of the liquid with the lower boiling point are formed first, and at a constant temperature, whole of the liquid changes into vapors. The vapors are condensed by using a condenser, and the liquid is collected in a receiver placed at the open end of the condenser. The vapors of the liquid with higher boiling point that are formed later are also condensed, and the liquid is collected separately. Simple distillation cannot be used in the separation of liquids which do not differ much in their boiling points. Another technique called fractional distillation is used to separate liquids which have small difference in their boiling points. In this technique, a fractionating column is fitted over the mouth of the round bottom flask. The purpose of the fractionating column is to increase the area of the cooling surface and to provide hurdles to the ascending vapors. The vapors of a liquid mixture are passed through this column before condensation. As the liquid boils, the more volatile component rises to the top. Some of the condensing liquid obtains heat from the ascending vapors and gets vaporized again, becoming richer in low boiling component. These vapors of low boiling component rise to the top of the column, becoming purer as they reach the top. The pure vapor is passed through the condenser and the liquid is collected in a receiver. The remaining liquid in the distillation flask becomes rich in high boiling component after a series of successive distillations. Each successive condensation and vaporization unit in the fractionating column is called a theoretical plate. The technique of fractional distillation is used in the separation of different fractions of crude oil in the petroleum industry. In the case of liquids with very high boiling points and liquids that decompose below their boiling points or at their boiling points, another method called distillation under reduced pressure is used for purification. In this method, the pressure on the liquids is reduced with the help of a water pump or a vacuum pump. As we know, a liquid starts to boil when its vapor pressure becomes equal to the external pressure. Thus, reducing the pressure on the liquid surface reduces the boiling point of the liquid. In soap industries, glycerol is separated from spent lye using this method. Another distillation process, steam distillation, is used to separate substances that are immiscible with water and steam volatile. That is, get evaporated when steam is passed through them. In this process, the liquid to be distilled is kept in a heated flask and steam from the steam generator is passed through it. The mixture of the steam and the compound is condensed and collected. The compound is separated from water using a separating funnel. In steam distillation, the liquid boils when the sum of the vapor pressures due to the organic liquid and due to water becomes equal to the atmospheric pressure. Since the vapor pressure of organic liquid is lower than the atmospheric pressure, the organic liquid vaporizes at low temperature than its boiling point. Hence, if one of the substances in the mixture is water and the other is a water-insoluble but steam-volatile substance, then the mixture will boil close to but below 373 Kelvin. Aniline is separated by this technique from an aniline water mixture. Differential extraction is a purification technique that is used to separate an organic compound present in an aqueous solution with the help of an organic solvent in which that compound is more soluble than water. The basic requirement of the organic solvent is that it should be immiscible with water so that the organic and water layers can be easily separated. Differential extraction is carried out in a separating funnel. In this method, the aqueous solution of the compound to be extracted is taken in the separating funnel. Then, a suitable organic solvent is added to the funnel. Next, the funnel is shaken for some time and then it is allowed to stand for some time. On standing, the organic compound and the solvent form two separate layers in the funnel. The organic compound being more soluble in the organic solvent goes into the organic layer. If the organic solvent is more denser than water, then it goes down and occupies as the lower layer in the separating funnel. The two layers are collected separately by opening the stopcock. The organic substance is recovered from the solvent layer by distillation. If the organic compound is less soluble in the organic solvent, then a technique of continuous extraction is used. In this method, a small quantity of the same solvent is repeatedly used for the extraction of the compound. The solvent layer is collected each time and distilled finally to get the compound. Another important method of identifying, separating, and purifying compounds of a mixture is chromatography. The name chromatography is derived from the Greek word chroma, which means color, and graphein, which means to write. The principle behind this technique is the differential adsorption of various components of a mixture over or on the fixed or removable phase called stationary phase under the influence of moving phase called mobile phase. In this method, the mixture of substances is applied onto a stationary phase, which may be a solid or a liquid, a pure solvent or a mixture of solvents, or a gas as a mobile phase is passed over it. The components of the mixture get gradually distributed between the two phases. Thus, the components in the mixture are separated from one another. Based on the principle involved, chromatography is divided into two types: adsorption chromatography and partition chromatography. Adsorption chromatography is based mainly on the differences between the adsorption affinities of the different compounds in a mixture on the commonly used adsorbents like silica gel and alumina. When the mobile phase is allowed to run over the adsorbent, the components in the mixture move by varying distances over the stationary phase. Based on the principle of differential adsorption, adsorption chromatographic techniques are of two types. They are, namely, column chromatography and thin layer chromatography. In column chromatography, first, the stationary phase, which is the adsorbent, is packed in a vertical glass tube. Then, the mixture of components to be separated is placed on the top of the stationary phase. An appropriate mobile phase or eluent, which is a liquid or a mixture of liquids, is allowed to run down the column slowly. During elution, the components in the mixture get eluted according to their adsorption strengths. The components which are weakly adsorbed are eluted first, and components which are strongly adsorbed are eluted later. Thus, complete separation of the components in the mixture takes place. Now let's look at the thin layer chromatography. Thin layer chromatography involves the separation of substances in a mixture using a glass plate which is coated with an adsorbent. In this method, a thin layer of adsorbent, preferably alumina or silica gel, which acts as the stationary phase, is coated on the glass plate. The plate is known as thin layer chromatography plate or chroma plate. Then, a small spot of the solution of the mixture to be separated is applied about 2 centimeters above the one end of the glass plate. Then the plate is placed in a closed container containing the eluent. As the eluent moves up the plate, it causes the components of the mixture to distribute between the adsorbent on the plate and the moving solvent, thus separating the components of the mixture. The relative adsorption of each component in the mixture is expressed in terms of its retardation factor, RF. The value of the retardation factor is determined by dividing the distance moved by the substance from the baseline by the distance moved by the solvent from the baseline. The retardation factor of a component is unique with respect to a stationary phase. Hence, any unknown component present in a mixture can be identified with the help of its retardation factor. The components are separated into separate spots, appearing from the bottom to the top of the plate. Depending on the degree of adsorption, the separation of the components takes place and leaves different colored spots when the compounds are colored at different levels of the plate. The spots of the colorless compounds, which are invisible to the eye, can be detected by placing the plate under ultraviolet light. Another method to detect the spots of colorless compounds is by placing the glass plate in a covered jar containing a few crystals of iodine. The colorless spots of the compounds which absorb iodine will appear as brown spots. Apart from these two methods, sometimes an appropriate reagent may also be sprayed on the plate. For example, amino acids are detected by spraying the ninhydrin solution on the glass plate. On spraying ninhydrin, the colorless spots appear mainly as purple or brown colored spots. Another type of chromatography is partition chromatography. This technique is based on continuous differential partitioning of solutes between mobile and stationary phases. It includes paper chromatography, where a special quality paper known as chromatography paper is used. Chromatography paper has water molecules trapped within it, which act as a stationary phase. Now let's take a closer look at the procedure. The chromatography paper is spotted at the base with the solution of the mixture to be separated. Then the paper is suspended in a closed jar containing a suitable solvent or a mixture of solvents. The solvent rises up by capillary action and flows over the spot. Depending on the differential partitioning of the components in the mixture, they get separated with the mobile solvent. Such a paper strip is called a chromatogram. The spots of the separated colored compounds are visible at different heights from the position of the initial spot due to their original color. The spots of the separated colorless compounds may be observed either under ultraviolet light or by spraying an appropriate reagent as done in thin layer chromatography. Carbon and hydrogen are the chief elements present in an organic compound. In addition to these elements, an organic compound may also consist of other elements such as nitrogen, oxygen, sulfur, halogens, phosphorus, and so on. The qualitative analysis helps to detect the presence of these elements present in an organic compound. Let us look at how the elements carbon and hydrogen are detected. First, the given compound is heated with the oxidizing agent cupric oxide. As a result, the elements carbon and hydrogen present in the compound get oxidized to carbon dioxide and water respectively. The products obtained are then passed over anhydrous copper sulfate and bubbled through lime water. We observe that copper sulfate turns blue, whereas lime water turns milky. Anhydrous copper sulfate absorbs moisture and turns blue due to the formation of hydrated copper sulfate, that is, copper sulfate pentahydrate. This indicates the presence of hydrogen. When the carbon dioxide formed in the reaction is passed through lime water, that is, calcium hydroxide, a milky white precipitate is formed due to the formation of calcium carbonate. This indicates the presence of carbon in the given compound. Now, let us look at the detection of other elements such as nitrogen, sulfur, and halogens. The presence of nitrogen, sulfur, and halogens can be detected using Lassigne's test. In Lassigne's test, a small piece of sodium metal is taken into a fusion tube and is heated to red hot. Then, the given compound is added to it in small amounts and the fusion tube is again gently heated to red hot. The red hot tube is then introduced into a mortar containing a few ml of distilled water. The red hot tube is crushed and the mixture is thoroughly grinded with the pestle. The contents are then filtered into a test tube. The filtrate obtained is called sodium fusion extract or Lassigne's extract. This extract is used to detect the other elements such as nitrogen, halogens, and sulfur. During fusion, the elements nitrogen, sulfur, and halogen combine with sodium and are converted to sodium cyanide, sodium sulfide, and sodium halide respectively. In other words, they are converted into their ionic forms. Carbon and nitrogen present in the organic compound react with sodium metal to form sodium cyanide. If sulfur is present in the compound, it is converted to sodium sulfide, whereas the halogen in the compound is converted to respective sodium halide. Now, for the detection of nitrogen, a small amount of sodium fusion extract is boiled with a pinch of solid ferrous sulfate and then acidified with concentrated sulfuric acid. The sodium cyanide reacts with ferrous sulfate to form sodium hexacyanoferrate 2. Ferrous ions are oxidized to ferric ions when heated with concentrated sulfuric acid. These ferric ions react with sodium hexacyanoferrate 2 to produce Prussian blue coloration of ferriferrocyanide, that is, iron 3 hexacyanoferrate 2. The Prussian blue coloration confirms the presence of nitrogen in the organic compound. There are two tests that help us to detect the presence of sulfur using sodium fusion extract. The first test involves the reaction between the sodium fusion extract and lead acetate, whereas the other involves the reaction between sodium fusion extract and alcoholic sodium nitroprusside. In the lead acetate test, sodium fusion extract is first acidified with acetic acid and later lead acetate solution is added to this mixture. This produces a black precipitate of lead sulfide, confirming the presence of sulfur. In the sodium nitroprusside test, the sodium fusion extract is treated with a few ml of alcoholic sodium nitroprusside. If the mixture turns violet, it indicates the presence of sulfur. The violet coloration is due to the formation of sodium thionitroprusside. If nitrogen and sulfur both are present in the organic compound, then on heating the sodium fusion extract with acidified ferrous sulfate solution, a blood red coloration is obtained instead of Persian blue. The blood red coloration is due to the formation of sodium thiocyanate ion 3, thus indicating the presence of both nitrogen and sulfur. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treated with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. In the test for halogens, sodium fusion extract is first boiled with dilute nitric acid. To this solution, a few drops of silver nitrate solution are added. The color of the precipitate indicates the presence of the specific halogen. A white precipitate, soluble in ammonium hydroxide, indicates the presence of chlorine. The white-colored precipitate is due to the formation of silver chloride. If the precipitate is pale yellow and sparingly soluble in ammonium hydroxide, then it indicates the presence of bromine. The yellow-colored precipitate is due to the formation of silver bromide. If the precipitate is yellow and insoluble in ammonium hydroxide, then it shows the presence of iodine. This yellow-colored precipitate is due to the formation of silver iodide. To detect the presence of phosphorus, sodium extract is heated with oxidizing agent sodium peroxide. And then treated with ammonium molybdate. If a yellow precipitate of ammonium phosphomolybdate is formed, it indicates the presence of phosphorus. First, let us see the method of estimation of carbon and hydrogen in an organic compound. Carbon and hydrogen in the organic compound are estimated by Liebig's method. The apparatus used for this method consists of a combustion tube packed with copper oxide pellets, a platinum or porcelain boat, 2 pre-weighed absorption tubes, and a burner. In this method, a known quantity of the organic compound is placed in the platinum or porcelain boat. The boat is placed in the glass combustion tube packed with copper 2 oxide pellets. One end of the combustion tube is connected to the oxygen supply, and the other side is connected to the 2 U-shaped absorption tubes. One of the absorption tubes contains anhydrous calcium chloride, while the other contains concentrated potassium hydroxide solution. Now, the combustion tube, along with the boat placed in it, is heated and pure oxygen is passed through it. As a result of combustion, carbon dioxide and water are formed. Water in the mixture is absorbed in U-tube containing anhydrous calcium chloride, and carbon dioxide is absorbed in another U-tube containing concentrated solution of potassium hydroxide. The U-tubes are weighed again after this absorption. The increase in the masses of calcium chloride and potassium hydroxide is calculated to get the amount of carbon dioxide and water in it. From the amount of carbon dioxide and water, the percentage of carbon and hydrogen are calculated. Let the mass of the organic compound taken be m grams, and the mass of the water and carbon dioxide produced be m1 and m2 grams, respectively. We know that 44 grams of carbon dioxide contains 12 grams of carbon. Therefore, the carbon content in m2 grams of carbon dioxide may be calculated as 12 multiplied by m2 divided by 44. Now, m grams of organic compound contain 12 multiplied by m2 divided by 44 and m. Therefore, 100 grams of organic compound would contain 12 multiplied by m2 multiplied by 100 divided by the product of 44 and m. This gives the percentage of carbon present in m grams of the given organic compound. The percentage of hydrogen is also calculated in a similar way. We know that 18 grams of water contains 2 grams of hydrogen. Therefore, m1 grams of water contain 2 multiplied by m1 divided by 18. Now, m grams of organic compound contain 2 multiplied by m1 divided by 18 and m grams. Therefore, 100 grams of organic compound would contain 2 multiplied by m1 multiplied by 100 divided by the product of 18 and m. For the estimation of nitrogen, 2 methods, the Dumas method and Kjeldahl's method, are used. In Dumas method, a known mass of an organic compound is heated strongly with coarse cupric oxide in an atmosphere of carbon dioxide. Carbon and hydrogen get oxidized to carbon dioxide and water, while the nitrogen present in the organic compound is converted into free nitrogen. A part of the nitrogen may get oxidized into oxides of nitrogen. When passed over a heated copper gauge, these oxides of nitrogen are reduced into free nitrogen again. The mixture produced, which contains carbon dioxide, water, and nitrogen, is collected over an aqueous solution of potassium hydroxide. This solution absorbs the carbon dioxide gas from the mixture, leaving nitrogen behind. This nitrogen is collected in the upper part of the graduated tube. From the volume of this nitrogen collected, the percentage of nitrogen in the compound is calculated. If the mass of the organic compound is m grams, the volume of the nitrogen collected is V1 ml at room temperature of T1 Kelvin. The atmospheric pressure is P and the aqueous tension at T Kelvin is P dash. Then, the pressure of nitrogen gas at T Kelvin is atmospheric pressure P minus aqueous tension P dash. Let this be equal to P1. Then, the volume of nitrogen at STP is equal to P1 mm multiplied V1 ml multiplied by 273 Kelvin divided by the product of T1 Kelvin and 760 mm. Let's assume that the resultant volume is Vml. As we know, 22,400 ml of nitrogen weigh 28 grams at STP. Therefore, Vml nitrogen at STP weighs 28 multiplied by Vml divided by 22,400 ml. Nitrogen is also estimated by another method known as the Kjeldahl's method. The method can be divided into 2 major stages, namely digestion and distillation. During the digestion stage, the nitrogen present in the organic compound is converted into ammonium sulfate. This is achieved by heating the compound in Kjeldahl flask with concentrated sulfuric acid in the presence of small amount of copper sulfate. Now, the contents of the flask are cooled and transferred into a distillation flask and heated with concentrated sodium hydroxide to liberate ammonia gas. This is the distillation stage. The ammonia produced in this process is absorbed in a known volume of excess of standard solution of sulfuric acid. Therefore, the amount of ammonia produced can be determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating the unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid reacted with ammonia. Let's assume that the mass of the organic compound taken is m grams. The volume of sulfuric acid of molarity m taken in the flask is V ml. The volume of sodium hydroxide of molarity m used for the neutralization of excess acid is V1 ml. As per the stoichiometric equation, V1 ml of sodium hydroxide of molarity m is equal to V1 by 2 ml of sulfuric acid of molarity m. The volume of the unreacted sulfuric acid of molarity m is equal to V minus V1 by 2 ml. V minus V1 by 2 ml of sulfuric acid of molarity m is equal to 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m. From the equation, we get that this is equal to twice the volume of the ammonium solution of molarity m. We know that 1000 ml of 1 molar ammonia solution contains 17 grams of ammonia or 14 grams of nitrogen. Therefore, 2 multiplied by V minus V1 by 2 ml of ammonia solution of molarity m contains 14 multiplied by m multiplied by 2 multiplied by V minus V1 by 2 divided by 1000. Therefore, the percentage of nitrogen is equal to 14 into m into twice V minus V1 by 2 divided by 1000 and multiplied by 100 by m. It is important to note that Geldahl method is not applicable when nitrogen is present in the ring, as well as in nitro and azo compounds. This is because the nitrogen of these compounds does not change to ammonia sulfate under these conditions. Halogens are estimated by Carrier's method. In this method, a known mass of organic compound is to be heated with fuming nitric acid in the presence of silver nitrate in a hard glass tube called Carrier's tube. In this process, carbon and hydrogen are oxidized to carbon dioxide and water, while halogen is converted into silver halide. The halogen forms a precipitate of silver halide. This precipitate is filtered, washed, dried, and then weighed. Let the mass of the compound taken is m grams and the mass of the silver halide formed as m1 grams. 1 mole of silver halide contains 1 mole of halide. Therefore, the mass of halogen in m1 of silver halide is determined by dividing the product of the atomic mass of halogen and m1 by the molecular mass of silver halide. Therefore, the percentage of halogen is equal to the atomic mass of halogen multiplied by m1 multiplied by 100 divided by the product of molecular mass of silver halide and m. To estimate sulfur present in the given organic compound, a known mass of the organic compound is taken in a Carrier's tube and heated with sodium peroxide or fuming nitric acid. The sulfur present in the compound is oxidized to sulfuric acid. The acid is cooled and treated with excess of aqueous barium chloride solution. It gives a precipitate of barium sulfate. This precipitate is filtered, washed, dried, and then weighed for analysis. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of the organic compound taken be m grams. The mass of barium sulfate formed is m1 grams. We know that the molecular mass of barium sulfate is 233 grams. And the amount of sulfur in 1 mole of barium sulfate is 32 grams. Therefore, the mass of sulfur in M1 gram of barium sulfate is M1 multiplied by 32 divided by 233. Therefore, the percentage of sulfur in the compound is 32 multiplied by M1 multiplied by 100 divided by 233 multiplied by M. The quantitative analysis of phosphorus in the given organic compound is done by heating a known mass of organic compound with fuming nitric acid in a carrier's tube. As a result, phosphorus is oxidized to phosphoric acid. When this phosphoric acid is treated with ammonia and ammonium molybdate, a precipitate of ammonium phosphomolybdate is formed. Sometimes, phosphoric acid is precipitated by adding magnesia mixture. Magnesia mixture is obtained by dissolving 100 grams of magnesium chloride hexahydrate and 100 grams of ammonium chloride in water. To this, 50 ml of ammonium hydroxide is added and the solution is diluted to 1000 ml. On adding magnesia mixture to phosphoric acid, a precipitate of magnesium ammonium phosphate is formed. This precipitate is filtered, washed, dried, and then ignited to produce magnesium pyrophosphate. From the weight of magnesium pyrophosphate, weight of phosphorus can be estimated. Let the mass of the organic compound taken be m grams and the mass of ammonium phosphomolybdate be m1 grams. The molecular mass of ammonium phosphomolybdate is 1877 grams. Atomic mass of phosphorus is equal to 31 grams. Therefore, the percentage of phosphorus present in the compound is M1 multiplied by 31 multiplied by 100 divided by the product of 1877 and M. If phosphorus is estimated as magnesium pyrophosphate, then the percentage of phosphorus is equal to 62 multiplied by M1 multiplied by 100 divided by the product of 222 and M. Here, M is the mass of the organic compound taken. M1 is the mass of magnesium pyrophosphate formed. 222 is the molar mass of magnesium pyrophosphate and 62 is the mass of 2 phosphorus atoms present in magnesium pyrophosphate. For the quantitative analysis of oxygen in an organic compound, a known weight of the organic compound is heated in a stream of nitrogen gas. As a result, the organic compound gets decomposed. Then, the oxygen-containing mixture is passed over red-hot coke, where all the oxygen is converted to carbon monoxide according to the equation shown. This gaseous mixture is passed through warm iodine pentoxide when carbon monoxide is oxidized to carbon dioxide, producing iodine. This reaction may be represented as shown here. To make the amount of carbon monoxide produced in the first equation equal to the amount of carbon monoxide used in the second equation, multiply the first and second equation with 5 and 2 respectively. It is clearly evident from the equation that 1 mole of oxygen liberated from the compound produces 2 moles of carbon dioxide. Thus, 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated. Let the mass of the organic compound taken be m grams. Mass of carbon dioxide produced be m1 grams. We have seen that 88 grams of carbon dioxide is obtained if 32 grams of oxygen is liberated, and then m1 grams of carbon dioxide is obtained if 32 into m1 divided by 88 grams of oxygen is liberated. Therefore, the amount of oxygen liberated from m grams of organic compound is equal to 32 into m1 divided by 88 multiplied by m. Hence, 100 grams of the compound produces 32 multiplied by m1 multiplied by 100 divided by the product of 88 and m. This gives the percentage of oxygen present in the compound.